All right, so Mr. Wickline, we are going to, in this lesson, we're going to cover uncertainty in measurement, which includes rounding, significant figures. I'll do some calculation examples, but we'll also just quickly cover scientific notation and also estimation. I think estimation is one of the big ticket items in this lesson, but a lot of the stuff, including rounding and significant figures, you'll use all year. So I'm going to draw some stuff in on this slide that looks like it didn't transfer, and I'll get back to you. Okay, so one of the things that we're going to be doing in class in following this lesson is going to be these questions. You don't need to do them now. Just you can write down the title for a homework, and these are the ones we'll do. And again, we're going to be studying uncertainty in measurement and scientific notation. So here's my quick notes on this slide. Accuracy and precision are actually not really the same thing, even though we use them very similarly in real life. Accuracy is actually how close the average measured value in a group of measurements is to the true value. So if you use a dartboard analogy, then these three darts right here in the center of the dartboard, they are really, really close to the true value or the bullseye of the dartboard. So that means that they're averaging out to the true value. Now up here, these guys, they're not in the center, and they're not averaging out to the true value either. So that's not going to be very accurate. These guys, although they're really close together, they're not averaging out to the center, which is in here somewhere. So this is also not accurate. And confusingly, I think, these three are not very close together. But if you think about this is a triangle, and the center of that triangle being there, then they actually do average out. So that means that this one's accurate and this one's accurate. So I'm going to go ahead and write a little A in. A little ACC for accurate. Then we have this idea of precision. And precision is when a group of measurements are similar to each other. A good example of precision could be here, because the darts are all really close together, and also here, because the darts are really close together. So I'm going to go ahead and write in like precise right there, and also precise. And, just for the record, this one's not precise, and neither is that one. Accuracy and precision are important in physics because accuracy and precision relate to the instruments that we use to measure any kind of data about an object, whether that's velocity or acceleration or mass or volume. We're going to have to use an instrument, and those instruments are going to have different amounts of accuracy and precision, very different. So we have to keep track of those things at all times, and in this lesson I'm going to teach you some of the ways that we keep track. Quick review on rounding. When you're rounding a number, oftentimes you'll be directed to round to a certain digit. In this question, I'm asking you to round to this 8, but actually the digit that matters more is the 7. You need to use the 7 to round the 8. So if I'm going to, let's see, where do I need to write that number? Using the rule above, round the number to the nearest 10th. That's this digit. So that means that the 8 is going to be rounded according to the 7. So I'm going to write 243.9, and that would be my answer to that question, because the 7 is above 5, so that means that this 8 gets rounded up. So uncertainty is this concept that revolves around the measurement of values using real instruments, and those real instruments have error. But I would say that uncertainty is a concept that you're going to need to think about all year. And it has to do with quantities that are being measured. So the measurement always consists of some digits that are certain plus a digit whose value has been estimated. That's the way it works when you're measuring anything. You're going to have a lot of digits that are definitely true, and one digit at the end that is an estimate. So every measurement has some uncertainty, and the uncertainty could result from the quality and the limitations of the instrument. Like, are you using an instrument that's made of cardboard, or is it made very precisely? Also, the person who's measuring the quantity could be really bad at what they're doing, so that's going to limit things as well. And just keep in mind that if several measurements are taken and those measurements are really similar to each other, then we call those measurements precise. But if those measurements average out to be really close to the actual value, that's when we call the measurement accurate. So, for example, we're going to check out Earth's gravity here. Now, Earth's gravity really is, in actual truth, 9.81 by meters per second squared. You can find that on the first page of your reference table. But let's say that a student measures the quantity as 9.98. Then they try it again and they get 9.98 again. And they try it one more time and get 9.99. How would we describe the measurements in terms of their accuracy and precision? You can pause the video and think about this and then come back. So if you said that these values are really similar to each other and therefore they are precise, then you are correct. They are definitely precise, but they're actually not accurate because they don't average out to be the actual value. On a practical level, when you're using uncertainty to make your own measurements, this is kind of how you would do it. And my example here is a thermometer. So it's pretty easy to see that the reading on this thermometer is above 5. And it also is definitely above 6 if you're looking at this carefully. But it appears to be just below 7. So the thing that I'm certain of is that this temperature is above 6. I'm not really sure how much it is above 6. And that's going to be my estimate part, but the certain part is the 6, and the estimate is just how much is it above 6. Generally, when we're not sure, like how much above, a whole number the other number is, we'll just throw a 0.5 on the end, and that's our estimate. I understand that some of you aren't going to like that, because this thermometer does not appear to be at the 0.5 mark between 6 and 7. But just keep in mind that if you don't have any marking there to really give you a 100% certainty of what it is, then you probably need to go with whatever's in the middle. In this case, 0.5. So the correct reading that I'm going to give is 6, which is what I'm certain of, 0.5, and that's my estimate, degrees Celsius. And that is going to be 2 significant digits in my answer, because significant digits on this slide are things that are all the certain digits plus 1 estimated. So here's my certain, there's my estimated, so that means that I have 2 significant digits. There are some traditional rules for counting significant figures. I'll go through these relatively slowly. Basically, when you look at a number and you want to know how many significant figures it has, pretty much every number is going to follow, you'll have to use these 3 general rules to evaluate it. And then if that number does not have a decimal, then you'll also need to think about this rule. And if that number does have a decimal, then you'll need to think about that rule as well. So my first example is to check out this value, 0.0025. What I would say in general for all numbers is that you need to start counting from the left with the first non-zero digit. So I'm going to start counting from the left, which is over here. The first non-zero digit is not that, not this, not that, because those are all zeros. This is the first non-zero digit. So this is the first one I count. And then you just count until the end. So the 2 and the 5, those are both the digits that I'm counting. I put a little over bar there just to show myself which ones counted and which ones didn't. My second rule is that any digit that's not a 0, or all digits that are 1 through 9, automatically count. So that means that all of those digits are definitely significant. And I'm putting an overbar to show all of those. So some zeros do count, and they would have to be between digits that are not zeros. So like you see this 3 and this 5. That means that these 3 zeros actually can count because they're between the 3 and the 5. So zeros between non-zero digits, 1 to 9, are automatically significant. So I will put an overbar above all of those. Those are all significant. So those are the rules that you use on just basically any number. Now, if that number also is a number that, let's say, does not have a decimal, then you can use this rule as well. The rule states that zeros at the end of the number are not significant. So, for instance, here's 3,500. It does not have a decimal. There's no decimal in this number. And that means that these 2 zeros at the end don't count. So I'm going to say that this 3 and that 5 are significant, but not the 2 zeros that follow. Now things change a little bit if the number includes a decimal. So if you do have a decimal, then zeros that follow the non-zero are significant. That doesn't mean you should be counting this one or this one, because these 2 zeros are basically the same as this guy right here, where you skip the leading zeros. These leading zeros are the same thing. There's leading zeros here, same thing there, they're not different. So I'm going to skip those 2 zeros and I'll start with the 7. But this rule for a number that has a decimal says that the zeros that follow the 7 count. So that means that the 7 definitely counts and the 0 after it counts, but not the zeros before. So in short, the number of significant digits in each of these values is 2, 4, 5, 2, and 2. So some people would call this Atlantic Pacific rule to be a simpler version of what we just discussed. I'm just going to consider a couple of numbers. I'll apply the rule, and you can decide which one you want to use. But here's 0.710 and 1040. 0.710 will solve over here, and 1040 will solve down there. So basically, the Atlantic Pacific rule asks you to recall some pretty basic geography. On this side of the United States, we have the Pacific Ocean. On this side, we have the Atlantic. The Atlantic is on the right-hand side, basically. Pacific is on the left. And we're not just trying to be cute with the geography. The P in Pacific is going to stand for present, and what we're referring to is the decimal. The A in Atlantic is going to stand for absent, and we're referring to the decimal again. So for instance, we'll use the Pacific rule on that guy because we have a present decimal. And we'll use the Atlantic rule for this one because we have an absent decimal. So what are these rules? The Pacific rule says that if the decimal point is present, then you need to start counting from the Pacific side of the number and skip any zeros that begin the number, but then once you get to your first non-zero, just count until the end. So for instance, how many significant digits are in 0.710? I'm going to skip the leading 0, but I'll start with the 7, and I will include the 1 and the 0 that are at the end. So there are 3 significant figures. So one more time, since the decimal point was present, I started counting from the beginning with the first non-zero digit, 7, and then I count until the end. So likewise, if the decimal point is absent, you're going to count from the Atlantic side, starting with the first non-zero. So like right here, or in 1040, it's absent. So I'm going to start counting from the Atlantic side. That's the right-hand side. And I'm going to skip any zeros that start the number. So I'm going to skip that 0. But I'll use that 4, and then I'll go 1, 2, 3. So I'll just mark those really quickly, but not the 0. And there are 3 significant figures. Let's do some sample problems now. What I think you guys should do is pause the video copy down these values and write the number of significant digits that you think each one of them has to the side of that value. Kind of do what I did, where you will put an overbar over the digits that you think are significant, and then ultimately just say how many there were. And also, I want you to answer this question down here, which is to explain basically the difference between this number and this number. So pause the video and copy and answer these questions. Okay, so here are my answers. If you get something that's different than one of these and you'd like to ask about it, just make sure that you make a mark in your notes and that you remember to ask in class. And then, verbally, I would say that down here, the difference between 2.07 and 2.070 is that this number clearly has more certainty because it has more digits, and it has more significant digits. I just said it, and that gives it more certainty as well. So when we use significant digits in calculations, you are going to have to distinguish between whether you're doing a multiplication division or an addition subtraction, because they actually do have different sets of rules. You're going to need a calculator for this slide, so take a moment and get that now. You can just pause the video, get your calculator. But I'll walk you through how to do these things. So starting with this first question, which is just calculating the volume of something. Pretty simple equation. You just need to do length times width times height. When you're doing these multiplication questions, this would go for division as well. You need to find a raw answer, but you also need to figure out how many significant figures are in each one of the values that are going into the number, because whichever one of these has the fewest sig figs, that's going to be how many sig figs your answer gets to have. So in the case of this guy who has 4, and this guy who has 3, and this guy who actually only has 2 sig figs, then my answer ultimately will only get to have 2 sig figs. So take a moment right now, pause the video, and at least get a raw answer and write it on that second line. So my raw answer was had several digits in it. I'm getting 4.806.9. The unit is going to be a kind of meter, but there's 1 meter, 2 meters, 3 meters. They're all being multiplied, so I'm going to go with meters cubed. There's my dimensional analysis. And remember, I said that my final answer can really only have 2 sig figs as per that value right there. So I'm going to get to keep the 4 and the 8, but no other digits. And I'm going to write 4.8 meters cubed. So that's how you do multiplication and division questions. But let's say that you have an addition or a subtraction. Then in that case, we're not really going to use significant figures or significant digits. Instead, we're really only going to look at decimal places. Whichever input has the fewest decimal places is going to be the one that limits your answer. So for instance, this guy right here, who has 0 decimal places, is going to have the most effect on the answer. So this guy has 1 decimal, no decimals, 3 decimals, and 2 decimals. So when we get our raw answer, we'll adjust it to have the same number of decimals as this guy. So pause the video and add up these items and write down your total. Okay, I just added them up. I got a raw answer of 2540.091. And my answer gets to have exactly 0 decimals, just like that input. So these 3 decimals have got to go. I'm going to take them out, and I have 2540 grams. All right, I'm going to write in some information that's missing on this slide, and I'll come back. Okay, guys, so on this slide, the thing that really matters here is that Calculations involving intermediate steps, like this one, which is an addition and a division, and this one, which is a subtraction and a multiplication, are questions that have intermediate steps. So calculations that involve intermediate steps, they don't have numbers rounded off to sig figs until the final answer's been reached. So you can use all your rules, just don't cut off any decimals along the way until you're finished. One thing I do is I use an overbar without cutting off decimals to keep track of the decimals as I'm going. So for instance, let's do the first one. When you do 35.6 plus 2.4, I believe you get 38. But remember, it's an addition, subtraction, so I need to have the same number of decimals as the two numbers that made it. So that has one decimal and that has one. So I'm actually going to write 0.0. And all of those count. And then I have a fraction bar, and it's over 4.803. So you can just do a division just like normal. And I'm getting 7.91172 and so on and so forth. But we have 3 significant digits there, and we have 4 here. So my answer actually only gets to have 3. It's going to be based on that number, and it's going to be those 3. So I'm going to write my final answer as 7.91 liters. Similarly, in this question below it, we have a subtraction, and also we have a multiplication. So if you just carry through the subtraction like normal, what you get is, I believe, 12.528. But remember, we need to have an equal number of decimals here as we have there and there. So this number only has 2 decimals. So that means that when I'm counting significant figures, I'm going to stop after that 2, and that the 8 won't be significant. But remember, don't round it off just yet. Wait until the end. So in the next step, you need to multiply it by 2.542. You can go ahead and just do that as normal. I'm getting 31.846 and more digits as well, but I'll stop there. And my unit's going to be square meters, because it's going to be this meter times that meter. And in terms of sig figs, this number has 4 sig figs and this one has 4. So I'm going to give 4 to my final answer. And I'm going to go with 31.85 square meters. So hopefully that made sense. And you can ask in class if it didn't. So a lot of you guys already know how to do scientific notation, which is amazing for me. But just let's do it like as a general idea. Scientific notation are numbers that follow this format. This value A is some number that is larger than 1 but less than 10. In other words, it has 1 digit that is to the left of the decimal, and an infinite number of possible digits that are to the right of the decimal. And then you have a times 10, and then that n is an exponent. It could be 0, 1, 2, 3, 4. It could be a negative number as well. No rules on what n can be, but it should be an integer. Let's take a look at this question. The mean radius of Earth is 6,370,000 meters. How many significant figures are in the value above? I'm seeing only 3, so not counting really any of those zeros, and that's because the decimal was not showing. So I'm just going to go with 3 significant figures. In terms of scientific notation, it's going to be something like 6.37 as my value for A. Remember, you can only have one digit to the left of the decimal. And the exponent, we'll have to be clever about that. We can go ahead and put in the times 10, because that's required. But to the what is going to depend on how many spaces you move the decimal. So the decimal was sort of invisibly right here, and it looks like we moved it 1, 2, 3, 4, 5, 6 right there. So it looks like we moved it 6 places to the left. So I'm going to put an exponent of 6 there. So 6.37 by 10 to the 6. And how many significant figures are in the value I just calculated? Again, it's really the same answer. It's just going to be these 3 digits there. In fact, the rule is if you are looking at a number in scientific notation, all of the digits that are in the A value are considered significant. So it's going to be 3 significant figures. So estimation in physics, this is like a really big deal. Believe it or not, you're going to have to estimate like objects' length, their weight, all kinds of different things. And there are some tricks that can help you make those estimates. For instance, you need to have a decent sense of what a kilogram is. A kilogram is 2.2 pounds. Now, one thing that's interesting is, in order for this to make any kind of sense to you, you actually have to have a good sense of what a pound is. If you need a reference for that, you can base it on some cans of soup. So basically, you might know that big fat can of soup, the Progresso soup, if you have 2 cans of it, that's about 1 kilogram. So that means that if you have 2 cans of Progresso soup and it's 1 kilogram, then that's also about 2.2 pounds. Or in other words, each can of Progresso soup is about 1 pound. So that can help about, on a lot of questions. Here's another piece of advice. A quarter or a nickel, both of those, quarters and nickels, have a mass of just about 5 grams. 5 grams is the same as 0.005 kilograms, and that's based on just metric conversions of going from gram to kilogram, which is a larger unit. Newton, which is a force unit, or a unit that we could even use to measure weight, which is different than mass. A Newton is just about the same weight as a medium apple. That is to say, not a large apple, not a small apple, a medium apple. And also maybe a large egg. A large egg would have a weight of just about 1 Newton. Now, all my my average Regents physics students have legs, and your leg is going to be about 1 meter in length. Other things that are about a meter could be the distance from the floor to the doorknob on a door, or a baseball bat. A baseball bat would be about a meter. So basically anything that's about as long as your leg is about a meter. So take a moment now, pause the video, and consider these questions right here, and see if you can come up with an answer for both of them. You don't need to write them down in your Cornell notes, but you need to have some mental answers. Okay, so the object that weighs just about 1 Newton, I'm going to go with a golf ball, because that's pretty similar in size to a medium apple or a large egg. Circle which height above the floor that an average doorknob is. So the doorknob is about the length of your leg, which is about a meter. And one of these values is the same thing as a meter. That value is going to be this one. Came out looking really weird in this slide, but it was supposed to be 10 to the 0. For some reason, that exponent got pulled down. So 10 to the 0 meters is the same thing as 1 meter. So that's definitely the answer. And how many quarters are in a kilogram? So keep in mind that a quarter is about 5 grams. And 5 grams is equal to 0.005 kilograms. If you multiply this number by 200, you will get 1,000, 1 kilogram or 1,000 grams. So I think the key part of my answer here is the number 200. It would take 200 quarters at 5 grams each to get to 1 kilogram. So this pair up in summary, I think it's actually pretty easy. What I'd like for you to do is pause the video and read the questions and consider the answers. You will need to calculate data for the very last section. So you can get out a calculator and calculate data, make sure you have those answers. Okay, so I plugged in my answers. Keep in mind, accuracy is when your average of all your data values is close to the actual, and precision is when those data values are close to each other. So, for instance, group 1 had these data values right here. Those data values are averaging out to be a 12, and I can see that here in the mean. So, group 1, you're accurate. But your values are really far away from each other. So that means that group 1, since your range is large, group 1, you are not precise. So group 1 overall, you're accurate, you're not precise. In group 2, I would reverse those claims. I would say that in group 2, you are precise because these values are close to each other, but you're not accurate, meaning that when I average these numbers, they come out to 11.4, and in the question I stated that the yarn is 1 foot long. So it's 12 inches and 11.4 is not 12. So inside these blue circles are actually negative exponents. What I want you to do on this slide is actually to copy down the questions and answer them to the best of your ability. We will go over the answers in class. You just need to ask me, prompt me to do that, and we will do that. And then all the answer choices that I circled have negative exponents, which are really hard to see. I'll zoom in to give you a really blurry idea of what I'm talking about. So now you may see these very faint negative exponents. So when you're looking for the negative exponent, I think you're kind of just going to be looking for a smudge, and that's why I found smudges here and in both of those. So I went ahead and circled in blue all the ones that look like they have negative exponents to me. Just keep that in mind because that will totally affect your answer. So that concludes the lesson. Make sure you have Cornell notes finished for tomorrow.